All right, I guess it's a good point to start. Welcome back, everyone. This is the third lecture of our course on infrared symmetries in general relativity. So, Aguiar, symmetries, and GR, lecture 3. And I guess before we start, are there any questions you would like to ask now? Okay, it doesn't seem so, but as always, you can interrupt me if you want to ask anything. So as a quick recap of what we've been doing so far, our goal is to understand BMS symmetries. Here an open mic. Are there any questions? Okay, I guess no. So our goal is to understand BMS symmetries, which are the symmetries of asymptotically flat spacetimes when you get to infinity. So these are symmetries in the deep infrared region of asymptotically flat spacetimes. And in order to do that, what we have done so far is to understand the basic ideas behind group theory, which was essential for us to understand how to mathematically formalize the notion of a symmetry. And this is the general theory that applies to. Sorry, there's something. No, okay, no. It's just some notification that appeared in my computer. Anyway, so we started seeing how group theory can allow us to describe what are symmetries, so how groups describe collections of symmetries. And this is the general theory that you're going to use in any branch of physics. So group theory can be used in general relativity, of course, but also it plays a very significant role when you're doing, for example, particle physics, condensed matter physics, and many other things. So a few important groups that we discussed here were SO3, which is a group of rotations. So these here are rotations without reflections. Without reflections. And the basic definition for this group is that it is composed of matrices that are 3 by 3. These are real matrices. They satisfy the orthogonality condition. So they are orthogonal matrices. And also, they have positive determinant. Oops. That R equals plus 1. So this is the definition of SO3. This is the prototypical group we started with to motivate the definition of groups in general. And later, we considered a few more complicated groups, which were the Lorentz group, SO plus 3, 1. This here are the 4 by 4 real matrices, which preserve the Minkowski metric. They have unit positive determinant, and the first element on the upper left corner is positive. So this here is what defines a general Lorentz matrix. This here guarantees that you do not have any time reflections, so you don't have time reversals. And this here, along with this condition, ensures that we don't have spatial reflections. So these two conditions here are what guarantee that we don't have reflections. So this is the simplest form of the group. This is a single connected component. And we can build up the whole Lorentz group by using this piece alone. After that, we also discussed the Poincare group, which is ISO plus 31. And this guy here is composed of pairs lambda A, where lambda is an element of the Lorentz group, and A is a translation. Something particularly important that we also saw is that the Poincare group can actually be written as a semi-direct product of two groups. So it is SO plus 31, semi-direct R4. So this here are the translations, this here the Lorentz transformations, and this expression here means that a general Poincare transformation can be written as a composition of a translation and a Lorentz transformation in a very specific way. After that, we went to study maps between manifolds. And we discussed, for example, what are maps between manifolds. So we had a manifold M, and we had a map going to a different manifold N. And we discussed, for example, how to do pullbacks and push forwards, which is a way of carrying a tensor or even a tensor field from one manifold to the other. There are specific rules on how you can do that. So, for example, vectors can be pushed forward, but they cannot be pulled back. And one-forms can be pulled back, but not pushed forward. The exception to this rule is when phi happens to be a diffeomorphism, because in this case, you can, for example, you can pull back a vector by defining that this is actually you're actually carrying these things with the inverse. So you're actually making the push forward with the inverse. And this allows you to make a few more general constructions. The main point about this discussion that I want to recap here is that we also managed to make what we call the tangent map, or also I call it the push forward, but in different geometry you can also call it the tangent map. My notation for push forward was up. This is the push forward, and here we have phi pn. So this here is the differential or the tangent map or the derivative of the map phi. So it is this. Sorry, let me just say something here. Okay. So this here is the differential or the derivative or the tangent map or the push forward of the map phi. So we can understand this here as the derivative in a similar sense to what we do in calculus on Euclidean spaces. So it's similar to what we would get if we were working with maps between Rm and Rn. It would be the very same thing, and this guy here would be the Jacobian matrix or something like that. So this is the basic idea. We will need to recall this notion here for a minor comment, a minor but important comment that I'll make later. And the most important thing from last class, aside from the Poincare group, was our discussion of the Lie derivative. So this is a notion of derivative that we can use to in any manifold, and it consists in this expression here. So we make a push forward with minus t of the tensor minus the original tensor over t. And this here is the definition of the Lie derivative, and this is sort of the basic idea behind this in a more sketchy way would be that this is the tensor at the point plus t minus the tensor at the point divided by t. So this expression here makes this expression here rigorous and meaningful, because this expression here below doesn't really make sense until you tell how exactly you can evaluate t at p plus t, and how can you bring it back so they are both tensors in the same point, because you cannot compare tensors in different points in your manifold, and stuff like that. So this here is the way to do this in a mathematically meaningful way. And this notion of derivative is available in all manifolds. This is not like the covariant derivative, which you must add by hand. So if you start, for example, with, suppose you start with the manifold R4. This here is a manifold, so you have a notion of how to take derivatives, of how to calculate integrals, of how to do calculus in R4. So this is a manifold. But now you can put many different metrics in R4. And each of those metrics is going to lead to a different covariant derivative. So for example, the most basic one you could pick, if you are doing relativity, of course, it would be the Minkowski matrix. So let me just write it like this. So this is the Minkowski matrix. This is one of the options you have, but it is not the only one. So for example, we could consider the metric for a star. The metric for a star would be something with this appearance here. It's 1 minus 2 m of r over r minus 1 the r squared plus r squared and the angular term. So these two are metrics on R4. They are both valid metrics on R4, but they are very different. And in particular, they lead to different covariant derivatives. So depending on the metric you choose, you're going to have a different covariant derivative on R4. However, the lead derivative does not care about that. The lead derivative is the same regardless of the metric you choose. The lead derivative only depends on the manifold. And this was important for us because we wanted to discuss symmetries and the natural notion of symmetry, of a local, of an infinitesimal symmetry in relativity, in a manifold, to be more general, is exactly that the lead derivative of some tensor with respect to some vector field, actually, I'm sorry. Yeah, this is another important difference between the covariant derivative and the lead derivative. For the covariant derivative, you can always consider an object like this by using a single point. So you only need to know v at a single point to calculate this expression. While to compute the lead derivative, you actually need a vector field. It is not enough to have a vector at a single point. There is a question in chat. Let me take it. We are implicitly taking the covariant derivative to come from the Levi-Civita connection, right? Otherwise, the metric would have nothing to do with it. That is correct. So for those of you who don't know, the Levi-Civita connection is the unique differential operator, if you want to use this nomenclature, in the manifold, such that this thing here holds, and also such that it is torsionless, which means that you can commute the covariant derivatives on scalar functions. So these two conditions here define what we call the Levi-Civita connection. It is written like this. And connection is a term from differential geometry which usually refers to more complicated structures known as bundles, but that doesn't really matter here right now. And yes, usually when you're general relativity, in particular, the discussion I'm having, I'm assuming this to be the Levi-Civita connection. But if you prefer, the arguments I just gave can also be made by considering different connections, different derivative operators. It's actually the same thing. So, so you could also use different derivative operators in R4, even if you do not have a metric. So indeed, there are slightly different things. You have slightly different freedoms in here. But it is usual within Riemannian geometry and pseudo-Riemannian geometry and general relativity to take this condition here. But you have more general theories of gravity that do not take this and use more general derivative operators. But indeed, in these lectures, I'm always going to be working with the Levi-Civita connection. Oh no, actually, there are a few situations in which I won't, but it's because we will be dealing with spacetimes that are a bit weird, and then you don't have the same structure. You don't have they're not pseudo-Riemannian manifolds, but we will get to that later. At this point, yes, I was mentioning the Levi-Civita connection. So the Lie derivative is a very different construction, and to impose an infinitesimal symmetry on a tensor field, actually, and this could be, for example, the metric. What you do is that you impose that the Lie derivative of the tensor field with respect to some vector field is 0. So this vector field generates the transformations generates transformations, not necessarily the transformations, that keep T invariant. So as an example, if you have a spherically symmetric spacetime, it will hold that the Lie derivative with respect to psi of the metric is 0, where psi is this vector here. And phi is the angular coordinate. So this could be, for example, you have a black hole here, and then you have this angular coordinate phi here. And this vector is going to be a symmetry of the metric because you have a spherically symmetric metric. So in this situation, you have this example, for example. Another situation is you may have a static spacetime, in which case you have this here, where psi is the time-like vector. So these two simple examples. These are examples that occur, for example, in the Schwarzschild black hole, and these are the basic ideas. And when a vector v satisfies this equation, we call it a Killing vector or Killing vector field. And you have a slightly more general definition as well, which is that of a conformal Killing vector field, in which you can inflate the metric. So this here is what we call a conformal Killing vector field, or CKV for conformal Killing vector. If you open up the definition or the expression for the Lie derivative in terms of covariant derivatives, the expressions for these two equations are going to be this here for the Killing equation, and this here for the conformal Killing vector equation. And the reason for this factor here is that this is actually equal to lambda. You can show that lambda must be this expression. So we have these two definitions of particularly important vectors in your spacetime, which are going to give you what are the symmetries in your spacetime. So this here are symmetries of the spacetime. They are isometries of the spacetime, and this means that they preserve the metric. So they preserve the whole metric of the spacetime. That means, for example, that when you do this sorts of transformations, you're going to take mg, which is your spacetime, to m prime g prime, and this is actually the same thing. We are not making any changes. A conformal Killing vector field, a CKV, is slightly different. It preserves what we call the conformal structure. So what happens here is that if V is a CKV, then this induces a one-parameter group of diffeomorphisms, and this one-parameter group will act on the metric by means of a conformal transformation. So you change the metric, but you just inflate it. And this means that you still have some structure that is preserved, but you do not preserve the whole metric. But this is important in some applications. Even though it is weaker than isometries, there's also important transformations, and they are called conformal isometries. I think it is useful to give an example at this point. So we'll make a case study, which are the conformal Killing vectors of the sphere S2. So this is the two-dimensional sphere, which is the usual sphere you all know and love. It is a submanifold of R3. So just to make sure everyone understands what we're talking about, this is defined by the points in R3 such that x2 plus y2 plus z2 equals 1. So this is the unit sphere, the unit two-dimensional sphere, which you can think of as living in R3, but we're interested only in the intrinsic structure of S2. So we won't care about the R3, we care only about the sphere. The metric for the sphere is very well known, and it is given by, I'm going to use this notation for the metric on the round sphere. It is given in spherical coordinates by this expression here, which you may know from any space-time written in spherical coordinates. You always have an expression that looks like this if it is spherically symmetric. So this here is the metric for a sphere. These are in spherical coordinates, but for us, it would not be particularly convenient to walk in spherical coordinates. Instead, we're going to choose to walk in something called stereographic coordinates. This is a different choice of coordinates in the sphere, and we're going to take it for the simple reason that they are easier to handle in the calculations that we will be performing. It is easier to calculate the conformal Killing vector fields in the sphere within stereographic coordinates. And how do we define these coordinates? The basic idea is the following. You pick the sphere, and I'm going to draw here a plane that cuts the sphere at the equator. Okay, so this here is at the equator. And I'm going to assign coordinates to each of these points on the sphere in the following way. I'm going to pick a point, say here, and then I'm going to draw a line from the North Pole to the point and keep extending it until it cuts the plane at some point, let's say here. Then I'll assign to this point here the coordinate zeta, which equals to x plus I, y in this plane here. So I have here my two coordinates, which are x and y in my plane. So this here is coordinate x, this here is coordinate y. And at this point here, we have coordinates x, y, and I'm going to give the complex coordinate zeta to this point here. This is going to be x plus I, y. This is the stereographic coordinate at this point. So this point here is going to be described by a complex coordinate. And you can, of course, think of it also as the pair zeta bar. And this here assigns a coordinates to each point. There are a few important comments in here. You should notice that each point in the sphere is going to lead to a different point in the plane. The south pole is at the origin at the plane. So the value zeta equals 0 is at the south pole. And you may notice that when you're going to find a coordinates for the North Pole, you have an issue because the North Pole a line from the North Pole to the North Pole doesn't really cut the plane, it isn't really defined. So in fact, the coordinates at the North Pole would be zeta equals infinity. This is actually complex infinity. And this here is the North Pole. So a coordinate system breaks at the North Pole. Recall that a coordinate system must give finite values to all coordinates, and here we are violating this at the North Pole. You should notice that since we're using complex values, this here is a way of mapping all of the complex plane to the sphere, and we have an extra point, and this point is precisely infinity. So this is actually a way of seeing the sphere as what we call the Riemann sphere, which is the complex plane plus a point at infinity. This is what we call the Riemann sphere. It is the simplest example, well, the second simplest example of what is called a Riemann surface, which is a one-dimensional analytic complex manifold. So that is a different construction. It's not something we usually use in general relativity. In relativity, we usually work with real manifolds, and the structure of smooth manifolds and the structure of analytic manifolds is ridiculously different. So they're very different things. But this here is a particularly important example for the calculations we are going to discuss. Can the point at infinity be covered with a different chart that connects with the stereographic chart, or is it always mapped to infinity? You will always have some point at infinity. So you cannot cover the whole sphere with a single coordinate chart. And the reason for this can be thought of as topological. The one way of seeing this is that you're trying to make a map from S2 to, let's say, R2. You can also think of the complex plane, if you will. But this is what you do when you're doing a coordinate chart. And what happens is this here is a compact topological space, and this here is not compact. But compactness, the property of being compact, is a topological invariance. So you cannot find any homeomorphism, any continuous function with continuous inverse that is actually going to be from S2 to R2. So you always have at least one problem. You always have at least one point that doesn't work. This is one of the possible arguments for this, and this is the reason one of the reasons we can't have a perfect map of the Earth. So when you make a map of the Earth, you will always have some sort of distortion. So, for example, in the Mercator projection, you're going to have very large portions of land, things extremely distorted near the poles. So you have always this giant mass of Antarctica here, and you have a gigantic Russia, while in the middle you don't have this much distortion. So for example, in the Mercator map, Greenland looks like nearly the size of Africa, but actually Greenland is 14 times smaller than Africa. And one of the reasons for this is precisely this here. You cannot have a continuous with continuous inverse map between both of them. Another explanation for this would be what we call the Gauss-Bonnet theorem, which is a result in classical differential geometry, but I will not get into this. If not with a single chart, can we make an atlas out of two charts with diffeomorphic boundary in the stereographic projection? Yes, we can find two charts. Two charts are possible. So what we can do here is we made one stereographic chart, which was in this fashion. We take line starting from the North Pole and going until the plane. We can do a similar chart by picking the same plane here, but now making lines that start at the South Pole. So in this fashion now, for this guy here, we have, let's say, psi equals 0 at the South Pole. The South Pole, no, sorry. Psi equals infinity at the South Pole, but psi equals 0 at the North Pole. So using these two charts, you get an atlas. And then you can describe the whole sphere by using these two coordinate systems, by using these two charts. So it's possible to cover all of the sphere with charts, and that needs to be possible, both because the sphere is a Riemannian manifold and because the Riemann sphere is a Riemann surface. So you need to be able to do that, otherwise there wouldn't be the structures. So you can indeed do this, and this will be important in a few minutes. So we have this choice of coordinates, and the natural question to ask now is, how does the metric look in this coordinates? And the answer is, it looks like this. So gamma here is going to be my notation for the metric of the sphere. So instead of using GAB for the metric of the sphere, I'm going to use always gamma AB, just to make sure, to make clear that I'm talking about the sphere. This here are the components of the metric, and you have this factor 2 here because you're taking the off-diagonal components. So this metric here, this looks like 0, 0, gamma zeta, zeta bar, gamma zeta, zeta bar. So if you prefer to understand this 2 over here, you can just think that what we're writing is actually gamma zeta, zeta bar. Sorry, I should reverse one of these guys, but they're actually equal because the metric needs to be real. So you can write it like this, plus this. And this guy's here commute, so you can just join everyone, and it holds that this guy needs to be equal to this guy, both because gamma needs to be real and because the metric is symmetric. So this is the metric, and this component gamma zeta z bar, zeta zeta bar, is given by this expression here, 1 plus zeta zeta bar square. The Christoffel symbols for this metric and this coordinates are given by gamma zeta 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 equals minus 2 zeta bar over 1 plus zeta zeta bar, and this is the complex conjugate of the other non-vanishing Christoffel symbols. The other ones vanish. So these two are the only non-vanishing Christoffel symbols that we get. And now we want to discuss what are the conformal killing vector fields. So what are the CKVs in this manifold, so in the sphere? And the expression for the CKVs is going to be this expression here. So y is my vector field, since we are dealing with a two-dimensional manifold, n becomes 2. So this here doesn't appear. We have this here. It is a bit more convenient to write this in this notation. It just gets a little bit easier to compute, but there's nothing wrong if you want to use the equation on top. Both of them are going to work. You choose whichever one you are more comfortable with. I think this one here is a bit more straightforward when you're carrying out the calculations, but you can open up both of them and see for yourselves. When now we take and evaluate each of these things here in coordinates, what we're going to find using those expressions for the Christoffel symbols and for the metric, you will find that this equation here is actually equivalent to the following equations. We have this derivative with respect to zeta of y, zeta bar equals 0. Then we have derivative with respect to zeta bar, y zeta equals 0. And here at the bottom, we have this here, which gets a little bit complicated. Zeta bar, zeta bar, zeta bar. This is y zeta bar. Plus the same thing with zeta, and this here is equal to the divergence of yc. So something that is important to be noticed, the first comment that I need to make is that this equation here is trivial. This expression here is just is always, regardless of what is the vector y, this is always equal to this expression here. So this is just the definition of the covariant derivative expanded in coordinates. So there's nothing really interesting happening with this equation. This equation is trivial. What matters for us, what is really important, are these two equations here. Now, the first thing I should notice is that for ya to be a real vector, to be real, we need that y zeta bar equals to y zeta with a bar. And the reason for this is that ya can actually be written as y zeta del zeta plus y zeta bar del zeta bar. And now if I take the conjugate of this guy, I should get the very same expressions. And this ends up requiring, since due to the fact that zeta is complex, we end up needing that these guys are equal. Is this correct? Yes, this is correct. Because when you take the conjugate here, you're going to get this here, and then you need this to be equal to this and this to be equal to this, so that this is equal to this, and the vector is real. So we have this condition, and thus the equations we're interested in derivative with respect to zeta of y zeta bar equals 0, and derivative with respect to zeta bar of y zeta equals 0. So these here are actually, these two are actually the same up to complex conjugation. So these are actually the same thing. Something that should be pointed out here is what we mean by the derivative with respect to the complex conjugate. I'm not sure if all of you have seen these details about complex calculus before, but this here are what we call Wirtinger derivatives. So this is a way of defining the complex derivative, and the basic definitions are the following. If zeta equals to x plus yz, then we define that the zeta is equal to f of the dx minus y the dy, and the conjugate is defined in the same way, except that you take a conjugate. Okay, so this is the definition of this complex derivatives. And something that is important here is that if you have this condition, let me use for a general function here. If you have this condition here, this means that f is analytic. And this means that f of zeta can be written as a Taylor series starting from 0. And this is actually a Taylor series, so let's just use this in the notation for Taylor series. This here, zeta n over n factorial. Okay, so this condition implies this thing here. You can write it as a Taylor series. So looking at these equations, we see that what they're telling us is precisely that this guy here, this component of the vector, is actually can actually be written as a Taylor series. So far, CKV in a sphere, the vector YA is a CKV in the sphere, means that Y zeta can be written as a Taylor series, starting from 0. So this is the most general conformal Killing vector field we have so far. Is there something I'm forgetting to mention? Yeah, it's okay. And of course, since we have that condition that Y zeta bar equals to Y zeta bar, knowing this guy here is enough for me to know all of the components of the vector field. Recall that we're working in 2 dimensions here. So a vector only has 2 components when you're walking in the sphere. So this is what we have so far. And the question is, are all of these solutions indeed conformal Killing vector fields? Because notice here that there are infinitely many of these guys. So there are infinitely many vector fields with this, infinitely many linearly independent vector fields with this appearance. So are indeed all of these guys conformal Killing fields? And the answer is no, because if we want a complete conformal Killing field, so we don't want something that only holds locally, we want something that holds globally at all of the sphere, then things got a little bit more complicated. Because you see, there is the issue we talked about earlier, a little while ago, that our coordinate system broke. And here, this here was infinity. The North Pole is mapped to zeta equals infinity. So our coordinate system breaks there, which means that we cannot trust our results. We cannot trust this thing here when we get close to infinity. So how can we know whether this here still makes sense when we get close to infinity? And the answer to that is we pick a different coordinate system. So we're going to pick a different coordinate system here that now takes infinity to be at the South Pole. And now the North Pole is a regular point because we inverted the way the coordinate system is defined. So now we take it's that idea. We started taking lines from the North Pole, and now we're taking lines from the South Pole. These 2 coordinate systems are related. You can show that at home by this expression here. So this is what we call an antipodal map. The 2 coordinates are antipodally related to each other, which means that if I had some value of zeta at this point, the same value of zeta will now be assigned to psi on this point. So you see, for example, here that infinity was taken to the other side of the sphere. It's now here, and 0 was also taken to the other side of the sphere. So we have this antipodal relation between both of them. This gives you a different map. And now, what are the coordinates that we find here? Notice that in these coordinates work just the same as the other stereographic coordinates that we chose, because there's nothing in the sphere that is particular about the North Pole or the South Pole. Those are just arbitrary conventions on what we call the North and South Pole. Any point of the sphere is equal to any other point in the sphere. So those equations we wrote earlier, in particular, this equation here still holds. And what is the new expression that we get for y psi when we make a coordinate transformation from y zeta? And the answer is using a coordinate transformation, we find that y psi is actually given by if we started with y zeta equals to alpha zeta n, so consider this particular vector field. You can just take sums of many vector fields of this form to get the general case. So if you start with this guy here and you do a coordinate transformation, what you will find is that you are taken to this guy here. And the most important thing to be noticed is that this here is not analytic. It cannot be written as a Taylor series. And the reason is that depending on the value of n, so for some values of n, you're going to have this guy here in the denominator. And if it is in the denominator, you cannot write as a Taylor series. So for example, if you try to write the function 1 over x as a Taylor series in x around 0, you will fail. That is not possible. And the reason is that this function is not analytic there. In fact, it's not even continuous at x equals 0. So it has no chance of being analytic. What you can do instead of a Taylor series, what you can do is something that is called a Laurent series, which is a more general type of series, which is of this form here. You now have negative integers as well in your series. This is called a Laurent series, and it is very used in complex calculus and complex analysis. So the issue we have here is now that not all values of n lead to something analytic. So which values of n do we still have something analytic? Well, the smallest value of n is n equals 0. And in this case, this expression here is going to have xi, 1 over xi to the minus 2. And this is actually just xi to the 2. So this is okay. This is analytic. For n equals 1, we have 1 over xi to the minus 1. This is xi, and this is analytic. For n equals 2, we have 1 over xi to the 0. This is 1. This is analytic. For n equals 3 or more, then we're going to have 1 over xi over n minus 2. And this here, we now have n minus 2 being a positive number. So now this is not analytic. I'm going to be lost on how the n minus 2 appear. Could you repeat that briefly? Yes, I didn't show the complete calculation. What you do here is you start with this conformal Killing vector field. So if you take all of the conformal Killing vector fields of this form, the alpha isn't really that important. So you can just pick this form here, just zeta to the n. All other conformal Killing vector fields, all other candidates to conformal Killing vector fields can be written as sums, possibly infinite sums, of fields with this coordinate components. Because the general solution would be something like this, would be a Taylor series. So we just sum fields with this general appearance, and we get the general solution. But if we make a coordinate transformation from this coordinate system to the xi coordinate system, which is the different stereographic coordinate system. So the original zeta coordinate system started at North Pole and had a pole, an infinity at the North Pole, and the new coordinate system with xi has infinity on the South Pole. So now it is regular at this North Pole. So when we make this coordinate transformation, what you find after you open up the calculations, I didn't open them up in here, is that y xi, the component y xi, is given by this expression here. And the issue is that you see that at infinity, so when you are near the North Pole, which is located at xi equals 0, you see that not all values of n lead to an analytic component. But you need an analytic component for it to be a conformal Killing vector field. So since not all values are analytic, you see that not all values of n are lead indeed to conformal Killing vector fields. And when you check for a few values of n, you see that for n equals 0, 1, and 2, you do have analytic components. but for n larger than or equal to 3, you no longer have an analytic component. And this means, yeah, sorry, I do need the alpha in here, I just recalled, because alpha can be complex. So I'm not taking only real combinations, I'm actually taking complex combinations. So what we find at the end, let me know if that was not clear. If you understand, that's okay. Okay. So what we find then is that the CKVs are going to be given by y zeta equals to 1 zeta squared I zeta and I zeta squared. It is always understood here that y zeta bar equals y zeta overall bar. And I have this guys here with imaginary units because I want to get only real fields at the end of the day. And using the 6 conformal killing vector fields, I can make linear combinations to get to any conformal killing vector field that I want to get in total. So this here are the conformal killing vector fields of the sphere. The global, the complete conformal killing vector fields. So you can discuss incomplete killing vector fields, which would be all of this guys here. I was told that this can play important roles in conformal field theories, but I knew nothing about conformal field theory, so I will not dive into that subject. But I think it is useful to mention. And this all the fields can also lead to important modern concepts known as super rotations. But I will not enter on this topic in this lecture. So I'm gonna keep to super translations, which are already difficult enough. So we have the 6 conformal killing vector fields, and then we can discuss what are the actual transformations they generate. So if we have the vector field YA, this should lead also to diffeomorphism phi t. And you can do that by picking a generic field with this form here. Okay, so alpha, beta, and gamma are just constants. And this here will give you a vector field. And the curve that you want, the transformation that you want will be given by d zeta in coordinates by d zeta dt equals to alpha plus beta zeta plus gamma zeta t. So this is how you get the because you are computing the curve that is everywhere parallel to the vector field, and that is going to give you to that. So zeta here represents the curve. When you take the derivative of the curve along its parameter, this better be the vector field because I want them to be parallel. So this here is a differential equation you get. Solving this differential equation, to my knowledge, is quite complicated, but Mathematica can do it. The general solution with all the details is far too complicated for us to even understand what it means. But the general shape of the solution is going to be given by this thing here, plus B of t over C of t zeta of 0 plus d of t. So this is the general shape of the solution. You have this initial values here, which are zeta of 0, and you have all of these functions a, b, c, and d, which are functions of alpha, beta, gamma, and of the time along the curve. And these guys here determine how exactly you are evolving. So this is the general expression, and the functional form of this functions of a, b, c, and d is actually way too complicated for us to focus on them. They're not really that important. But something important is that we can always choose to normalize these guys in such a way that AD minus BC equals 1. So you can always do this thing here. And what is interesting about this is that the transformation now that takes zeta of 0 to zeta of t, it has this shape here, which is given by this general expression. This transformation has a very specific name. It is called a Möbius transformation. These are exactly the only functions in the complex, and in the Riemann sphere, there are analytic everywhere, with the minor detail that you actually have to think of analytic in a different sense now, because you have infinity in your complex manifold. But they are analytic everywhere. They have exactly one pole. They have exactly one point where they give infinity, which is going to be this point here as zeta equals d over c, because this guy here vanishes. And you have exactly 1, 0 here, which is at zeta equals minus b over a, because this guy here vanishes. So you have exactly, you're always mapping, you are changing the coordinates so that you always keep exactly one south pole and one north pole. And this is the general structure that we have. So these are the general transformations. This is the general expression for the phi's that you get in this transformations. And notice that you had 6 conformal Kelvin fields, and now we still have 6 degrees of freedom here, because you have 3 complex parameters which determine all of these guys over here. Notice in particular that this is still true when we think about the parameters A, B, C, and D, because A, B, C, and D are 4 complex numbers. So 4 complex numbers equals 8 degrees of freedom, which might seem weird, but then recall that we imposed this condition here, this normalization condition, and that normalization condition takes out 2 degrees of freedom because it's one complex equation, and at the end of the day, we get 6 degrees of freedom exactly as we expected. So the next thing we may want to discuss here is how these transformations compose. So assume you have this transformation zeta to zeta prime, which is given by this Möbius transformation. And you have the transformation zeta prime to zeta double prime, which is given by this other transformation. And the question is, how does it take zeta to zeta double prime equals to a double prime zeta plus b double prime plus c double prime zeta plus d double prime? So what are the values of the double primes in terms of these guys here? And the answer is particularly interesting if you open up the calculations. Assuming, of course, that AD minus BC equals A prime D prime minus B prime D C prime equals 1. So assuming this, it holds that A double prime, B double prime, C double prime, D double prime can be written in matrix form, in this matrix here, and they're related to those other components by a simple matrix multiplication. So it's A, B, C, D. Notice, so we can write this here. Let's write this as the matrix double prime, this here as the matrix prime, this here as the matrix, and you see that we have just this product of matrices. Furthermore, notice that this condition here is telling me that M equals that M prime equals 1, since the determinant of M double prime equals to the determinant of M prime M, and this is equal to the product of the determinants. We see that we also get a matrix with unit determinant at the end, so it preserves our normalization conditions. And this is interesting because it tells us what is the group of conformal transformations in the sphere, which is the point that I'm the most interest to get in here, and in particular because we will use this later. And notice here that what we are dealing with here are complex matrices. So these are complex matrices. They are 2 by 2. And furthermore, they have unit determinant. So what we have is 2 by 2 complex matrices with unit determinant. This space here is a very known group, which is called SL2C. L means linear. So it just means that it is a group of matrices. And it has no other particular property. S, as before, means special, so the determinant is 1. C is, of course, because the matrices are complex, and 2 is because they are 2 by 2. So this is in principle the group, but there is a minor detail in here that is important to mention. These transformations are kept invariant under a transformation that takes all of the parameters to -1. So M is, let's write it here. Let's write it in this way. M is equivalent to -M. These two matrices lead to the very same Möbius transformation. So actually, the group you're dealing with is not SL2C. It is a smaller group that is just half of this group. In symbols, this is written SL2C, quotient with Z2. Z2 is the group that is composed only of +1 and -1, and the product is the usual product of integers. So this here is a multiplicative group. So this is the group, and this may seem completely weird, in particular because I never mentioned this group before, and now it is occurring out of the blue. So I should have mentioned this group in the group theory part. And the fact is, I actually did, but it is written in a very different way. Something that I find particularly impressive is that this group here is actually isomorphic to the Lorentz group in 4 dimensions. So the conformal Killing vector fields, the conformal transformations in the sphere actually generate, actually are given precisely by the restricted Lorentz transformations, by the proper orthogonous Lorentz transformations. So this is the group of global conformal transformations in the sphere. From this analysis, it is a bit more difficult to tell that if you impose also the condition, if you also impose this condition here, you would have a few more restrictions on your vectors. Let me just recall. Well, if you take again this guy here, alpha plus beta zeta plus gamma zeta 2. So take this field here and impose this condition. This will imply that beta plus beta bar is 0, and that gamma equals alpha bar. So you have these 3 conditions here. This corresponds to 3 real constraints. Is this correct? Yes, there's a 3 real constraints. So you have 2 constraints here, and you have a single constraint here. And the reason is because this guy here is actually telling you that the the real part of beta is 0. So you have 1 constraint over here, you have 2 constraints over here. In total, you have 3 real constraints, which means that for a Killing vector, not a conformal Killing vector, you have 6 minus 3 equals 3 degrees of freedom. So you have 3 Killing vectors on the sphere. This leads you to a 3-dimensional group, which is, of course, precisely SO3. To see that it is SO3, it is better to use the theory of Lie algebras, which I didn't mention in these lectures, and I will not, because it is a whole different board, which gets much more complicated than what we're dealing with right now. So we have this result on the sphere. There are a few calculations on my notes that show this, but I'm not gonna go over them to save some time. But in Minkowski spacetime, we can also do this analysis and compute what are the killing fields. I'm not interested in the conformal killing fields this time. I'm interested only in the killing fields because these are what will lead to the Poincare group. And then what we get, it's going to be 4 fields which have this expression here. I'm using Cartesian coordinates. So these are the 4 translations. These are the fields that generate the 4 translations. Then we have the fields that generate rotations. And I'm just going to write one of them here. The other one are similar. And it has this general appearance. So you see the other ones are going to be similar. You just replace X, Y, and Z by each other. And they're going to have this appearance in which you have a spatial Cartesian coordinate times a spatial Cartesian derivative. And you have this difference in sign between the two terms. So this here is what generates rotations. One of these guys, I think JZ is going to be equal when you change coordinates to spherical coordinates is going to be given by this guy here, which is the one we have been. I have been using as an example most times because it is the one that is easiest to write in spherical coordinates. And you also have the boosts and the general appearance they have is going to be something like this. So instead of having 2 spatial parts, you now have 1 time part because boosts involve both space and time. So they are a bit more, they are a little bit different. This here is a T, sorry. So this here is the general expression for boosts, rotations, and translations. And these are, you're going to have 10 killing vector fields. So you have 10 KVs. And this, of course, are going to generate the Poincare group, which is a 10-dimensional group. You can track a bit more of the details on the lecture notes. Okay, so this is what I had to tell about symmetries in Go spacetime. And now we're going to get to what is perhaps the most important part of these lectures, which is asymptotically flat spacetimes. So how do we define a spacetime to be asymptotically flat? And this will require a field asymptotically flat spacetimes. I will not go over all of the details in here, so I'm going to leave a few mathematical details out of the lecture. But I discussed the details in the lecture notes, and there you will also find good references to understand asymptotically flat spacetimes. I will focus more on the physical intuition behind each of the axioms that you put in an asymptotically flat spacetime. And to discuss that, I'm going to start by discussing infinity. So let's here discuss infinity in Minkowski. And here we are going to find the difficulty I mentioned, I think in the first lecture, that it is particularly weird for you to talk about infinity in curved spacetime because you don't have a clear way at first of how to get to infinity. When you know you are in Minkowski spacetime, you know that infinity should be something like R goes to infinity or something like this. But in a curved space-time, that would need a coordinate system. In fact, even Minkowski needs a coordinate system. And we would like to discuss infinity in a way that doesn't really rely so much on coordinates. So what we're going to do here is we will start by dealing with Minkowski spacetime in coordinates, in spherical coordinates. And the reason is because this spacetime is a spacetime we all know and love, and we understand in a much more intuitive way than more general spacetimes. So we start with Minkowski, using coordinate systems just to get a feeling of what we're doing. And later, we go on to give a completely coordinate-free definition of asymptotic flatness. To discuss this in Minkowski, we start with the Minkowski metric, which I'm going to write in spherical coordinates because they are the ones which make more sense for us to discuss infinity in here. And the reason is because if I want to talk about infinity, it seems a little bit more clear to discuss infinity by saying just that I take r to infinity, rather than discussing if I take x to infinity or do I take y to infinity. So r to infinity just seems a little bit more objective. It seems easier for us to work with. But you see, there are many ways in which I could go to infinity in Minkowski spacetime. So the first option is, of course, I go r to infinity. But I had other options as well. So for example, what if I chose to take time to infinity? This is another possibility. So I could choose either one of these guys. But let's be concrete. So let's choose r to infinity. But now I can take this limit in many different ways. So for example, am I taking r to infinity at t equals constant? Or am I taking r to infinity at u, which is retarded time, equals constant? Retarded time is t minus r. U is a very common notation in relativity for t minus r. It's used t minus r or variations of this. This is used, for example, in Eddington-Finkelstein coordinates in Schwarzschild black hole. But I'm using them in Minkowski, so it's just a shorthand for t minus r. So I could do this. I could do a different option in which I keep advanced time v equals t plus r equals constant. So which of these am I doing? Or am I doing a completely different thing? For concreteness, I will have to choose one of these guys. And the one that will be the most interesting for us turns out to be this guy here. So I'm going to use U constants. I think this one is the one which will lead to a richer theory and to clearer results, to more informative results. So in order to do this limit, the first reasonable thing for me to do is to write the metric in coordinates that use U. So instead of working in coordinates, in spherical coordinates with t as a time coordinate, I'm going to change this to spherical coordinates with u as a time coordinate. So let's choose to do this. When we do this, our line element, the Minkowski metric, is going to be given now by this expression here. This is just a change of coordinates. You can compute it at home. There's nothing really much complicated about it. Here, you just take this expression, use the du equals dt minus dr. So for dt, and replace it here, and you're going to find that expression. So you find this line element here. So now we can talk about what happens when I take the limit r to plus infinity. And we have a problem here, because if you pay attention to this line element, it seems that when I take r to plus infinity, this guy here diverges. So I have something that reminds me of a singularity. It is not really a singularity because there's nothing really physical or problematic about this. You see, what happens here is that when I take r to infinity, the area of a sphere with radius r becomes tends to infinity as well, because the area is going to be, by construction of the r coordinate, it's going to be 4 pi r squared. So in the limit in which r goes to plus infinity, the area of this sphere diverges. So I do have a geometric divergence in here, which just means that infinity is really far away and infinity is really big. So there's nothing fundamentally problematic with this, But for our purposes in which we want to take this limit very, very badly, it is difficult to deal with this. So we should try to do something else. Let's try to circumvent this by making another change of coordinates. So instead of working with the coordinate r, I'm going to define a new coordinate l, defined to be 1 over r. So with this new coordinate, I can just change coordinates again in my metric, and I'm going to find that the new metric will be given by this new expression here. So I have L minus 2 du dl plus L minus 2 ds2. And now the limit r goes to infinity is now equivalent to taking L to 0 from the right. So this is the case I'm interested in now. And infinity is at L equals 0. So I have the advantage that now infinity is at a specific value of my coordinate L. However, I didn't do any miracles in here. So when I take this limit, L goes to 0, this guy here still will diverge. So I need to do something else. I need to do something better than just change coordinates. Changing coordinates cannot do miracles, cannot really change the space-time itself. So I need to do something better. And what I will do here is a conformal transformation. So I'm going to inflate my metric by some factor. I'm going to define a new metric, G tilde AB, which is going to be given by L squared eta AB. So this guy here is the Minkowski metric. This here is the new metric. And this here is my conformal factor. Why is this expression interesting? Because in the limit in which L goes to 0, this guy here is diverging. The metric, the Minkowski metric, is divergent. So I'm multiplying it by something that goes to 0 when I take L to 0. So now I have a shot at having a finite expression as L goes to 0. I'm paying a price for this. And the price is that I'm now no longer working with the Minkowski metric. I'm actually working with this new conformally related metric. This is a different metric. It is not the Minkowski metric. But it is interesting for me because when I take the limit L goes to 0, this guy can remain finite. So what do we get for this metric now? What we get for this metric is the line element ds tilde squared, which is going to be given by just this line element here multiplied by L squared. Notice that L squared will exactly cancel this divergence here and this divergence here. So I have a great shot at having a finite thing. So this is going to be given by minus L squared du2 plus, did I write a plus over there? Yes, I wrote a plus, that's correct. Plus 2 du dl plus ds2. And there is the advantage, because now when I take the limit L goes to 0, nothing in here diverges. So this guy now makes sense. I can take the limit L goes to 0 from the right, and what I get there is going to be an induced metric, which I'm going to call the sigma. So this is the induced metric, induced on L equals 0. So at L equals 0, this guy here will be given by 0 du2 plus ds2. So notice that I have a metric that now has a vanishing component here. I only got rid of one coordinate, so I fixed L equals 0. So this means that I don't change L over my manifold, but I can still change U and the angular coordinates. The angular coordinates appear in the metric, but U, even though I can vary U over the surface with L equals 0, U does not appear in the metric. So this is a 2D metric in a 3D space, which is something particularly unusual, but also interesting. And the reason we have this feature here is because L equals 0 is actually what we call a new hypersurface. So this is a surface made of light rays. So it is not a surface that you can run over. You cannot really have particles propagating on the surface unless they are new particles, unless they are photons or gravitons. But you cannot have, for example, an electron walking on the surface because this surface is new. Everything that can walk on the surface either moves at the speed of light or doesn't move at all. So that is what we have. And it is interesting to notice that now we have L, the infinity is now at a can I say this? Infinity was brought in. It is now at a finite distance from us. It is now at arm's reach. We can now reach infinity. We can now touch infinity. And if I want to discuss, for example, how does a given tensor T, A stuff, B stuff, behaves at infinity, what I have to do is now just to evaluate this guy at L equals 0. There may be some difficulties here relating the tensor before and after, but the basic idea is that I'm just going to do this transformation, evaluate the tensor at infinity, and that gives me precisely how infinity behaves. So if I want to discuss now what is, for example, the electromagnetic field at infinity, I don't need to take a limit as we go to infinity. I found out a new manifold, a new space-time in which infinity is at arm's reach. So I can now reach infinity, I can now evaluate things at infinity. I brought infinity in. And this is the basic idea of how we work with infinity. So this is the way we deal with infinity in general relativity. This process is called a conformal compactification. And it was introduced, if I recall correctly, by Penrose. It is a technique he adapted from, I believe, algebraic geometry. So this is the basic idea, but we can do a compactification that is a little bit better than the one I just did. So for example, instead of working with the coordinates u, l, theta, phi, let's change and use the coordinates u, v, theta, phi, where I recall v equals to t plus r. In this coordinates, the Minkowski metric can be written as minus du dv plus 1/4 v minus u squared angular part. And why is this interesting? This is interesting because u and v are what we call new coordinates. It holds that if I take the vectors along their directions, so for example, this here, this is u, this is going to be 0. This is a new coordinate. And I find this interesting because I can now make a compactification while keeping the new character of this coordinate. How exactly do I do that? First, notice that for these values here, so I have u equals t minus r and v equals t plus r, we have that u and v obey these inequalities here. This middle inequality is because this guy here is t minus r, this guy is t plus r, and r is always greater than or equal to 0. So you have that v is always larger or equal to u. So this is the range we have. I would like to bring infinity in. So infinity for me is now located the places in which I take u to infinity or v to infinity or to minus infinity. And what I would like to do, this holds for all infinities that we had earlier. So if I want to take, for example, t goes to plus infinity, what I will be doing here can be understood as taking, for example, u goes to infinity at r equals constant. Because this here is going will mean that I'm taking t minus r to infinity as r is constant, and this is exactly what I wanted to do here. So all of those infinities can be understood in terms of u and v. So if I can bring in infinity for these guys, then I will have an infinity at an arm's length. And the way I can do that is with a compactifying function. So I can use the one I usually use. I'm just used to it using it, but it's not the only option. Is using a tangent. So I'm going to define big U in this way and big V in this way. Is this the only option? No. This here has the tangent goes from minus pi over 2 to pi over 2 to the real line. So this is how the tangent function operates. It is going to take the whole real line here is brought into this small interval. But I could also have used, for example, an inverse hyperbolic tangent, which has this domain and range. So this would be another possibility. Hyperbolic tangent is also quite used, but I'm just used to using tangent, and I always use tangent just for a personal preference. But there's nothing really, at least to my knowledge, there's nothing really different between both of them. You can use whichever one you want. So you're going to have this, and within these new coordinates, we now have this bound here. This middle bound here follows from this middle bound here, and the fact that 10 is crescent. Within these new coordinates, what we get now is the line element given by sec u squared, sec v squared, minus du dv, less 1/4, plus 1/4 sine square v minus u angular part. So this is the guy. And if you now take u and v to be very close to pi over 2 or to minus pi over 2, you will find that this factor here is divergent. Well, but now we know exactly what we want to do. Because if this is the factor that is divergent, we just have to get rid of this. And we can do that by using a conformal transformation. We know that the metric is exploding in this region. So we're going to add a conformal factor that will cancel this divergence. And this can be done by using a conformal factor given by 2 cosine u cosine v. This 2 here is just for convenience because it will cancel this 4 and we'll add a 4 in here. And this ends up being convenient to write in an acute way at the end. But it is not physically meaningful. You could just drop the 2 and you would still have the very same results. But using this conformal factor, we can now write the new metric GAV as being omega squared times the original metric. And this leads us to the new metric d s tilde 2, which is going to be minus 4 du dv plus sine square v minus u. To get a few coordinates that are slightly better, we're going to find t equals u plus v, big T equals u plus v, and big R equals v minus u. This is similar to how we had earlier, t equals u plus v over 2, and R equals v minus u over 2. We have these differences now in the factors of 2, but that isn't really much important. And I'm using this particular convention here just because it leads to a space-time that is very well known. So we have this transformation here, and the metric that we get in this new coordinates is given by this expression here. So we got this guy, and we have a few bounds on the values which are given by this thing here. So T and R for Minkowski spacetime, T and R are within this limit here. So notice that in particular, this implies that R must always be greater than or equal to 0. Now, why did I say that I wanted to put it in this particular form? Why I find this form interesting? Because this is a metric that is very well known since the first years of general relativity. This here is the metric for the Einstein static universe. So some of you may have heard that Einstein had a cosmological model in which he introduced the cosmological constant because he wanted to make the universe static. He didn't want to have a universe that was expanding nor contracting. And the way he figured that out was by putting in the cosmological constant. And this is the metric he arrived at. And something that should be mentioned here is that there is a great physical difference between this new metric and the original Minkowski metric. So eta, the Minkowski metric, Minkowski is a vacuum solution with no cosmological constant lambda. The unphysical metric, which is the Einstein static universe metric, has a fluid stress tensor with a cosmological constant. So these solutions, they are solutions for different stress tensors in the within general relativity. So the Minkowski metric is one solution for an empty spacetime with no cosmological constant. The Einstein static universe is a solution for a different physical scenario. It is a solution for a spacetime filled with fluid with a cosmological constant. So they solve the Einstein equations in very different scenarios. Hence, this metric in here is indeed unphysical. It is an unphysical metric, that it is only an auxiliary metric for us to discuss infinity. It is useful for us to discuss infinity, but it does not represent the physical spacetime. And something that is interesting to see here is that the Minkowski portion is conformal to this specific region here. So the actual Einstein static universe is larger. And there's always a nice picture to go with this discussion, which is the following. The Einstein static universe globally looks like the real line times three-dimensional sphere. So this here will be a four-dimensional manifold. It has this real line here corresponds to time, and this here corresponds to space. So space in the Einstein static universe is a three-dimensional sphere, just like what you have in some of the Friedmann-Lemaitre, Roberts, and Walker models. This is, in fact, one of the FLRW solutions. So this here is the global structure of the Einstein static universe for pictorial, due to pictorial constraints, we cannot draw a four-dimensional manifold, but we can try to draw a three-dimensional one. So here we're going to picture this guy here as a cylinder. I said a three-dimensional one, but this is actually a two-dimensional manifold. So this is a cylinder because around the cylinder you have an S1, and along the cylinder here you have an R1. So this here is time, and this here represents space. So the actual Einstein static universe is a bit more complicated because it has more an extra sphere. But we can focus here on this particular regime, and then you can draw, let's say here, that this here is measured by the big T coordinate, and this angle here is measured by the R coordinate. If you do this, then you can draw that region of the Minkowski spacetime in this way here. It's going to be a diamond. Okay, this bit here is behind the cylinder. Okay, so we have this yellow part here is in front of the cylinder, and the dashed lines are behind the cylinder. And I can just take this diamond here and flatten it out. If I flatten it out, I'm going to have something like this. And this point is actually equal to this point. Each of these pieces here is a different hemisphere. So what happens here, since I was hiding the extra spheres, what happens is that each of these points is half a sphere. So each of these points here is going to be something that looks like this. It is only half a sphere. It doesn't have the bottom part. So to make this a little bit simpler, many people, in particular me, usually draw this just as half a diamond, as something like this. Now, each point in here is a sphere. There is a few exceptions to this rule. So along here, this is the point with r equals 0. Each of these points in red is a single point. It is not a sphere. This point here, which we call I plus, is a point. This point here, which we call I0, is a point. And this guy here, which we call I minus, is a point. All of the other points in the diagram are spheres. They are not points, they are spheres. And they only look like points because we have restrictions when we are actually drawing this diagram. This is what we call a Penrose diagram. Or sometimes Carter-Penrose diagram. Also called conformal diagrams. Or block diagram. There are many different names for this. The most common one is probably Penrose diagram and then conformal diagram. But these are the names that they usually go with these sorts of diagrams. So this here is a picture of all of Minkowski spacetime. So this includes infinity. This is very different from a Minkowski diagram. So a Minkowski diagram would be something like this here, and we have t and we have x, and this diagram extends infinitely. So if you want to go to infinity, you have to, for example, take this direction and just keep going there forever. You cannot draw the whole diagram on a sheet of paper. This diagram is the whole space-time in a single compact drawing. So this here is the origin. The small r equals 0 and big R equals 0 are the same thing. This here is what we get in the region. This here is t plus r equals pi. This here is t minus r equals minus pi, and those coordinates we were using. But this particular coordinate values won't be very important for us. What is important is the physical significance of each of these regions. And we write them in this notation here. So we use I plus, I minus, I0, and this guys here we usually read as scry plus. So scry. So we have these 5 regions here, and these are the 5 regions of infinity. So suppose you start here at some finite point, and now you want to take a limit to infinity. So first, let's consider what happens when you take r goes to infinity at t equals constant. When you do this, you're going to reach I0. You always reach I0. So it doesn't matter from which point here you start, from which angle you start, you always reach I0, which is a single point. So there is only one point at spatial infinity. This is actually the name we gave it. This is spatial infinity. A different option that you might take would be to take t to plus or minus infinity at r equals constant. Then you would start from this point here. And if you go to plus infinity, you get an I plus. If you go to minus infinity, you get to I minus. This holds for all angular values, for all values of r. And remember, I plus and I minus are points. They are not spheres, they are points. So when you start at any point in the space-time and wait an infinitely long time without leaving that single point of r, so this means you are a time-like observer in particular, you will eventually, at infinite time, reach I plus, which is a single point. So all time-like geodesics end at I plus, and all time-like geodesics start at I minus. Is there anything else here that I would like to add? Yes, I was just forgetting what is the name of this guy here, but this is called future time-like infinity. And this, of course, is past time-like infinity. Now, there is another possibility, which is the most interesting one, which is when you do what I proposed at first, which is you take r to infinity while keeping u equals constant or v equals constant. If you choose to keep u constant, then you're going to reach from this point, you're going to go to this direction. And you eventually get to scry plus. Now, scry plus and scry minus are very different from the other infinities because I plus, I minus, and I zero are points. Scry plus and scry minus are manifolds. These guys are actually r times s2. So this is a manifold. This is a much more complex structure. And in particular, what this means here, r is the value of u, and s2 is the angular coordinate. So if I choose to start at a later time here, so for example, if I start at this point, I will reach scry plus at a later time at a different value of u. And if I choose a different direction, I will reach a different point in scry plus. So they are much more intricate than the other infinities. And this is the basic idea for this constructions, for these constructions of infinity and of of infinity in Minkowski spacetime. And now, in this last 15 minutes, I would like to discuss a bit. I'll probably go a bit short on this. And what are asymptotically flat spacetimes? I'm not going to give all of the details. You can find the details in the notes. But I'll give the main sketch of how you construct, of how you define an asymptotically flat spacetime. So we start with some spacetime mg. And we want to impose conditions on mg so that we can say that it is asymptotically flat. So we want to know what mg must satisfy so that we can call it asymptotically flat. And the main thing that we want is that it looks like Minkowski at infinity. Now, we just saw there are many different notions of infinity. So does this look like Minkowski at I plus? Does this look like Minkowski at I0? Does this look like Minkowski at scry plus? And we have many possibilities out of all of those. There are some of them that are more interesting than others. So for example, suppose you have a black hole. So I have a black hole here. And what happens here is that if I follow a light ray to infinity, I eventually will be very far from a black hole. And this indeed should lead to something that looks like Minkowski. So it should be something that has a new infinity that looks like Minkowski. Oh, yes, I didn't say, but scri plus and scri minus are known as future and past new infinities. If I go infinitely far by following a space-like geodesic, I eventually will get to something that looks like I0. Because I get very far from black hole, the gravitational field decays a lot, and eventually I'm quite far from the black hole. But if I go if I just sit here near the black hole and I wait for infinitely for an infinitely long time, I will never see a weak gravitational field because the black hole won't stop existing. I'm ignoring quantum effects, of course. But in classical general relativity, the black hole will never stop existing. If I'm sitting in a star, the field will never get weak. So asymptotically flat, flat, at I plus and minus, it's usually, and by usually I mean not always, interesting. There are scenarios in which this is interesting, or at least it is a useful assumption for you to prove theorems and stuff like that. But in most scenarios, this is not exactly interesting. You can also go, then we don't have the options of asking for asymptotically flat at square plus, at square minus, and at I0. And I plus minus, we are ignoring for now. Can we ask at I0? Yes, we can. But I0 is very technical. And the reason that I0 is technical is because when you make the conformal compactifications, I0 is not a point in which the manifold is move. And the reason is because things aren't typically related at I0. So consider, for example, the Coulomb field of electromagnetism, of EML. If we focus here on I0, what we have here, if we have a charge at the origin, then a positive charge at the origin, then the field here looks like this. It all points towards I0. And this means that it is not continuous across I0. Because if I cross I0 from this region to this region, I will see the field inverting its value. This, of course, it gets very small here, but you have this weird issues. And these difficulties make I0 a point very difficult to handle. And it can be handled, but it won't be our focus here, especially because it is very difficult to handle, and it won't be really important for our discussions. Can you discuss scri minus? Yes, scri minus is very similar to scri plus. It's just the same thing with a time reversal symmetry. So since they're both essentially the same thing, we can just ignore scri minus and we'll focus on infinity at scri plus. So we will discuss spacetimes that are asymptotically flat at future null infinity. To do this, what do we need to do? The first thing is, what is infinity? To ensure that we know what is infinity, we will make the same trick we did with the Minkowski spacetime. What we did there was we had Minkowski spacetime, M, and we found a larger spacetime, M tilde, which is an unphysical spacetime, and in which we could insert Minkowski spacetime inside. So this is the main idea we want. We want first that there exists some M tilde. What else do we need? We need that there is a function, a map from M to M tilde, which is what we call an embedding. In my notes, there is a slightly better definition of what is an embedding, but I'll just say that an embedding is, for our purposes, this is a diffeomorphism from M to the range of the embedding. Okay, so this is a function, a map that is smooth, that is injective, and if you pick the range, if you restrict the range of the embedding to, if you restrict the codomain of the embedding to its range, you get a diffeomorphism. You get something that is invertible with a smooth inverse. So this is what I'm going to call an embedding. And what this means here is that I have a copy of M inside M tilde. So I can actually find a copy of M inside M tilde, just like we did with the Minkowski spacetime. With Minkowski spacetime, what we had was that we had the Einstein cylinder here, and this region here, you can, let me just see how exactly I'm drawing this. Oh, okay, so this here. Okay, so and this diamond here, this diamond that is rolled up, this is actually R4. So we have here R times S3. This guy here you can understand as R4. So we actually get a copy of our spacetime inside the larger spacetime. Is this enough for what we want? And the answer is no. It is not sufficient to have a spacetime that fits inside another. I need them to have compatible metrics. So I need to have a metric that actually works as a conformal transformation. And for this, what I'm going to ask is that M tilde has a metric G tilde, which specifically on psi m equals to omega 2 times the push forward of GAB. So this here is just GAB as seen in psi m, because I made a copy of M, and to deal with this copy, I need to push the metric from M to the copy, and I get this guy here. This here is the metric in the physical spacetime. So this is the metric that I have in the surrounding spacetime. So in here I have G tilde, and this here means that inside the copy of M, these two metrics are conformally related. Is this sufficient for what I want? Still no. I want now to ensure that I get infinity. So I know that infinity happens when this guy here diverges. So what I want to do here is the following. I will ask that we have the following behavior. First, I'm going to define scri plus as being the boundary of M, of actually psi m. So I'm going to say that scri plus is this boundary here. This has a very precise definition within topology, which is an essential topic for you to discuss differential geometry. So when I say that I plus, that scri plus is the boundary, this is a very well-defined mathematical notion. So this makes rigorous sense. So it is precise. So I define that scri plus is going to be this boundary. This here is the symbol we usually use for boundary. It's the same as the partial derivative. So this is the boundary. And now that I define scri plus as the boundary, I'm going to ensure that I'm getting infinity, that this metric here is actually compactifying my spacetime by requiring that omega at scri plus equals to 0. So why do I want this? Because I want to have that effect. So I want to have that omega 2 psi star GAB actually goes to a finite value at scri plus. So this guy here will diverge at scri plus, this guy here will tend to 0 at scri plus, and the overall construction will go to a finite value. So I'm asking this thing here. There's also another thing that I want to ask about omega, which is the following. I want scri plus to be a hypersurface. So I want it to be a surface inside M tilde. And for it to be a surface, I need to ensure that the derivative that now I'm taking respect to the conformal metric of omega at scri plus is not zero. And the reason for this is that for me to have a surface, I would need that this here be this thing here is the normal to the surface. So this ensures that the normal is well defined, and this ensures that I have a single surface. So I have a single sheet of infinity. Because suppose we didn't have this, then what I could have, for example, which would be problematic, is that I didn't have a sheet squared plus. Maybe I have a block or something like this, and this is not a hypersurface. So I do not want to get this sort of thing because I want infinity to look like Minkowski. And for infinity to look like Minkowski, I better have that this guy here is actually R times S2. So I want to get to this. So you make these conditions. Is this everything we need? Not really. We need some additional assumptions that I'm not gonna discuss here, but you can find in the notes, which is first something we call strong causality. This is a condition that ensures that the space-time is causal in an appropriate sense. There are many conditions in general relativity which you can impose to ensure causality. Strong causality is one of the stronger ones. It's not the strongest one. The strongest one that I know of is global hyperbolicity, but we're not assuming this here. We're assuming only strong causality. And this is essentially to ensure that near infinity, the space-time is not very weird. So you don't have, for example, closed time-like curves near infinity. So you don't have time machines near infinity. The reason is because in Minkowski spacetime, you don't have time machines. And near infinity, I want it to look like Minkowski spacetime. So I'm going to ask this. There's a final condition that I need to ask, which is essentially, there is, I'm not going to write it here, but it is a technical condition to enforce that square plus is indeed R times S2. So this is going to be a condition that asks for completeness of the geodesics that composed square plus. And this is a slightly more technical condition. The complete condition is actually that, yeah, I'm not going to write. You can find in the notes. There's no point in writing it here. So these are the main ideas we need. So let me summarize them in a sketch definition. So definition, symptotically flat at no infinity. We start with a spacetime mg. Then assume that there is a conformal extension. So we have an M tilde. There is an embedding from M. Smooth. So I can copy M inside M tilde. I also asked for the range to be open, but this is again a technical condition. And there is a function from psi m, the real numbers. Actually, I can ask this here to be from M tilde to the real numbers, which is everywhere positive. Everywhere positive in the copy of the spacetime. This everywhere positive is to ensure that omega won't vanish at any finite point. And yes, the main point here is that it doesn't vanish. So we ask it to be positive because anyway, we will be writing omega 2 in front of the metric. So the sign doesn't really matter, and we don't want it to vanish because otherwise you would have a degenerate metric, and the metric would vanish at some point. So we ask this here, and we will impose the GAB at psi m equals to omega 2 times the push forward of the metric. So the metrics are conformally related. And now we assume these guys exist, and for asymptotic flatness at square plus, what we want is M is a manifold with boundary square plus. So a manifold with boundary is a slightly more complicated construction of a manifold, and it essentially means that it is a manifold with a boundary. So an example for this would be the plane with a boundary. So you consider here the plane, the archer plane, but only for positive values, and you assume that you have the x-axis. So this here is a closed interval. So you do have this point in the axis, but you see that this guy now is a weird manifold because it actually ends. And in here, at the boundary, you have something that is one-dimensional, while in here is something that is two-dimensional. This is the basic structure of a manifold with boundary. So in here, it just means that we are considering psi m to be this region here with the boundary at the boundary. So this is it. There are also a few more causality conditions in here that I'm not going to write. We asked for strong causality. Near square plus. We ask that omega at square plus equals 0, but its derivative is not 0. Oops. We ask for a technical condition that implies, in particular, that square plus equals R times S2. And there's a final condition that I didn't mention earlier, but I should have, which is that the vacuum Einstein field equations hold near square plus. This is, of course, because I wanted to be asymptotically flat. So if I had, for example, not a vacuum Einstein field equations, but instead, say, a cosmological constant, it wouldn't look like Minkowski. If I asked for this, for a cosmological constant, I would have something that is either asymptotically de Sitter or asymptotically anti-de Sitter, for example. And that is definitely not what I'm looking for here. So I need to get rid of those cases. There's a chance, I'm not fully sure, but I think that maybe some of the other axioms already took care of those cases. But in any case, to ensure that we have something asymptotically flat, so that it looks like Minkowski at infinity, I can have matter near infinity. So I need to have the vacuum Einstein field equations near infinity. This can be in an asymptotic sense. It doesn't need to be a neighborhood of infinity. You can use it in an asymptotic sense, but the main idea is that you need to have vacuum near infinity. And okay, that's almost everything I have for today. So it's starting to get some momentum back. But because I'm leaving some details out for you to check on the lecture notes. But we are at a good schedule. It's just a tiny bit, half a page that I didn't cover today, and we can perfectly cover it tomorrow. So I'm sorry for passing the time. Are there any questions you would like to ask now? Okay, there doesn't seem to be any, so I'll stop the recording and ask again.